Welcome back to the course on path planning and control of wheeled mobile robots. In the first lecture, we talked about the introduction of the course and organization. In this session, I will talk about the introduction of wheeled mobile robots. As you know, robotics is a very broad field of study. In this figure, shown from the Robot Park website, you can see the types of robots based on the locomotion method. Studying each of these locomotive methods requires several courses. In this course, we will just focus on wheeled robots. We won't even study robots with tracks. The basics of mobile robotics consist of locomotion, perception, and navigation. Locomotion system does not only rely on the medium in which the robot moves, but also on other factors such as maneuverability, controllability, train conditions, efficiency, stability, and so on. Perception is very important for an autonomous mobile robot to acquire information from its environment, sense objects around itself or its relative position. To achieve this, information are provided by the use of sensors and other related devices. The most important aspect in the design of a mobile robot is navigation abilities. The objective is for the robot to navigate from one destination to another, either in a recognized or uncontrolled environment. Most of the time, the mobile robot cannot take the direct route from its starting point to the ending point, which means that motion planning techniques must be incorporated. In this course, we will focus on wheeled robots whose locomotion is based on wheels. We will not have anything to do with its perception. Our focus will be on navigation and especially path planning and control. Without loss of generality, we will consider simplifying assumptions such as moving without skidding on hard, flat surfaces. Generally, wheeled robots consume less energy and move faster than other locomotion mechanisms, for example, legged robots or tracked vehicles. From the viewpoint of control, less control effort is required owing to their simple mechanisms and reduced stability problems. Also, it is difficult to overcome rough terrain or uneven ground conditions. Wheeled mobile robots are suitable for a large class of target environments in practical applications. These robots cannot pass obstacles, and this is the main disadvantage of this type of robots. Because of that, these robots are almost useless in terrains that are not flat and have low friction coefficient. A classification of wheeled mobile robots. The number of designs of wheeled robots can be infinite due to the following features: type of wheels, for example, conventional wheel, mecanum or Swedish wheel, omnidirectional wheel, and etc. The number of wheels, wheel arrangement, and wheel drive system. Now, I will introduce some types of wheels. They differ in their kinematics, and therefore the choice of wheel type has a large effect on the overall kinematics of the robot. The standard wheel and the caster wheel have a primary axis of rotation. As you can see in this figure, this is the conventional or standard wheel, and this is the caster wheel. They have a primary axis of rotation and are thus highly directional. To move in a different direction, the wheel must be steered steered first along a vertical axis. The key difference between these two wheels is that the standard wheel can accomplish this steering motion with no side effects as the center of rotation passes through the contact patch with the ground, whereas the caster wheel rotates around the offset axis. You can see the offset in this figure, causing a force to be imparted to the robot chassis during steering. Both of these wheels have 2 degrees of freedom. The mechanon wheel, which sometimes called the Swedish wheel or Elon wheel. Elon is the inventor of this kind of wheel. Is a design that is less constrained by directionally than the conventional standard wheel. It has a series of external rollers attached to the whole circumference of its rim. These rollers typically each have an axis of rotation at 45 degrees to the wheel plane and at 45 degrees to the axle line. The Swedish wheel functions as a normal wheel but provides low resistance in another direction as well. The small rollers attached around the circumference of the wheel are passive, and the wheel's primary axis serves as the only actively powered joint. The key advantage of this design is that also the wheel rotation is powered only along the one principal axis through the axle. The wheel can kinematically move with very little friction along many possible trajectories. One drawback of a mechanon wheel is that there is a vertical vibration because of discontinuous contact during motion. In order to solve this problem, a variety of mechanical designs have been proposed. Examples can be found in the literature. Another drawback is its relatively low durability when compared to the conventional wheels. Mechanon wheels have 3 degrees of freedom, and here you can see a movie shows the performance of mechanon wheels. You can notice the direction of these arrows. Omni wheels or poly wheels, similar to mechanon wheels, are wheels that small rollers around the circumference which are perpendicular to the turning direction. Mechanon wheel is also a type of omni wheel, with the exception that rollers are attached at 45 degrees angle around the circumference of another bigger wheel. The image at the top of this slide shows a mobile robot with 3 omni wheels. This is a schematic top view of the robot. Each wheel is controlled by driving the wheel forward or backward, and it is assumed that the wheels do not slip or skid in the driving direction. The rollers on the wheel allow free sliding of the wheel in the orthogonal direction. The robot that is shown at the bottom has 4 mechanon wheels which do not slip in the driving direction but allow free sliding at an angle of 45 degrees relative to the driving direction. The principle behind the omni-wheel and the mechanism wheel is the same, but they differ in the direction they allow free sliding. The spherical wheel is a truly omnidirectional wheel, often designed to so that it may be actively powered to spin along any direction. One mechanism for implementing this spherical design imitates the old computer mouse. Here in this picture you can see the spherical wheel, top view, side view, front view, and top view of a spherical wheel. We've looked at types of wheels in the previous slides. Let's look now at some common wheel arrangements. A typical example of one wheeled vehicle is the unicycle. A robot with a single wheel is basically unstable without dynamic control in order to maintain its balance of a body. Spherical robot can also be considered as a single-wheeled robot. However, single-wheel robots are rarely used in practical applications because additional balancing mechanisms are required and control is really difficult. Generally, there are two types of two-wheel robots, as shown in this slide. In the top, you can see a bicycle-type robot. It is common to steer a front wheel and to drive a rear wheel. Since the dynamic stability of a bicycle-type robot increases with its speed, a balancing mechanism is not necessarily required. The advantage of this approach is that the robot widths can be reduced. However, a bicycle type is rarely used because it cannot maintain pose when the robot stands still. In the bottom of the slide, a two-wheel differential drive robot is shown. It's possible to achieve static stability by accurately placing the center of gravity on the wheel axle. Some popular design examples for three-wheeled robots can be seen in this slide and the next slides. Since a robot with three wheels is statically stable and has a simple structure, it is one of the most widely used structures for wheeled robots. Figure A shows a two-wheel differential drive robot composed of two active fixed wheels and one passive caster wheel. So in total, the robot has three wheels. This is one of the most popular designs. Figure B shows a synchronous drive robot. This kind of robot can be built by using centered or off-centered orientable wheels. The steering and driving motions of each wheel are mechanically coupled by chains or belts. In this figure you can see the chains and belts, and the motions are actuated synchronously, so the wheel orientation are always identical. Here you can see another picture of synchronous drive robot. All wheels are actuated synchronously by drive motor. Here is the drive motor, and the drive motor defines the speed of the vehicle. All wheels steered synchronously by a steering motor. Here is the steering motor, and you can see the belt. This steering motor sets heading of the vehicle. The most significant advantage of synchronous drive robot is that omnidirectional movement can be achieved by using only two actuators. In this slide, figure C shows an omnimobile robot with mechanon wheels. Rollers around the wheels are not shown in this figure. Figure D shows an omnimobile robot with active caster wheels, and robot of figure E is an omnidirectional robot with steerable wheels. The famous four-wheel robot is the car-like robot. In most of designs, the front two wheels are synchronously steered to keep the same instantaneous center of rotation. In some cases, all wheels are steerable, as you can see at this figure. A major disadvantage of a car robot is that it is stable during high-speed motion. However, it requires a slightly complicated steering mechanism. If the rear wheels are actuated, a differential gear is required to obtain pure rolling of the rear wheels during the turning motion. A steering angle of the front wheel cannot reach 90 degrees. Therefore, parking motion control in a cluttered environment becomes difficult. Well, so far we've looked at the types of wheeled robots in terms of the number and type of wheels, as well as the arrangement of the wheels. However, there are still many other designs which we did not cover. Next, we will talk about the difference between wheeled and arm robots. This is done because most students usually have a basic familiarity with arm robots, which are also called manipulators. Let's first define two terms widely used in the robotics. The first term is pose. Pose of a robot is used to describe the position and orientation of a robot's end effector in the workspace. For example, in this manipulator, we can show the pose of the end effector using X, Y, and phi. X and Y shows, the pair X and Y shows the position of the end effector, and phi shows the orientation. And if we want to report the pose of robot, we should do it with X, Y, and phi. The next term is encoders. Encoders simply are devices that measure the angle of a joint. In wheeled robots, using the values specified by the encoders for the wheels does not lead to the detection of a unique pose for the robot, while in the case of the arms, pose of the end effector can be determined using the values of the joint encoders. In wheeled robots, the final pose depends on the selected path. And in the wheeled robot, we are facing a non-holonomic system. We will discuss this later in. To further explain the previous slide, let's consider an example. Consider the mobile robot in the home position. Its center of mass is shown in the figure. This is the center of mass. You can see two cases here. In the first case, the center of mass has moved as much as S1. Also, the right and left wheels have moved equal to S1R and S1L respectively. You can see that the final state or final pose final pose of the robot is here. In the second case, the center of mass has moved as much as S2. Also, the right and left wheels have moved equal to S2R and S2L respectively. You can see the final state of the robot in this case. Even though S1 is equal to S2 and the movement of robot's wheels is the same in both cases, S1R equals S2R, S1L equals S2L. But you can see that the robot is in different positions. This is what we call a non-holonomic system, and it is not seen in the case of an arm robot. Differential equations cannot be integrated to reach the final position in the case of a mobile robot. With the path traveled by each wheel, it is not possible to determine the final position. It must also be known how the path is traveled. You saw this fact in this slide. So if we have S1 S1R and S1L, we cannot determine the exact position of the robot. In fact, knowing the speed of each wheel relative to time is also an important issue. To explain this more, we will give another example. Here you see a planar 2R robot and a differential drive robot or diff drive robot. In the arm robot, Q1 and Q2 represent joint variables, and the pair Q1, Q2 represents the configuration space of the robot. The configuration space in this case can be represented as a two-dimensional plane. You can see that if a closed trajectory is traveled in the configuration space, the robot will return to the same initial position. In the right figure, you can see the robot. Q1 and Q2 are initially 0, and in this configuration, the robot is completely horizontal. Then Q1 and Q2 both reach pi over 2 in this pose, and we will have this configuration for the robot. You can see that if the joint variables return to the values at the beginning of the cycle, this is the cycle, the arm will eventually return to its initial position or initial pose. But there is another story about the wheeled robot. The left and the right wheel navigation angles form the configuration space of the robot. Here the robot first moves on a straight line, both wheels turn an equal amount. Then the left wheel remains fixed and only the right wheel turns forward. Then the right wheel remains fixed and the left wheel turns backward. Finally, the right wheel turns backward, arriving at the initial encoder values, which are 0. Yet the robot does not return to its origin. You can see the robot in the workspace in this figure, and finally robot returns to this configuration, not the first configuration. The first pose. You saw that performing a similar trajectory in the configuration space of a two-link manipulator, instead left the robot return to its initial position. But but this is not in the case of a mobile robot. In conclusion, a robot or a constraint is holonomic if a closed path in the configuration space leads to a closed path in the workspace, and it is a non-holonomic system if a closed path in the configuration space does not necessarily lead to its return to the initial state. So an arm robot is a holonomic system, and a differential drive robot is a non-holonomic system. Here are some of the difficulties of path planning for wheeled robots. As you have seen, the non-holonomic constraints of wheeled mobile robots impose difficulties for effective path planning. Presence of static or dynamic obstacles and the operation environments complicates the problem further. Path planning algorithms are computationally expensive, and this is one of the important challenges of path planning for wheeled mobile robots. Please think about this slide. Maybe we will discuss it in our next meeting. In the second chapter, in the next lecture, we will discuss forward and inverse kinematics of wheeled mobile robots. Thank you. Bye.